Okay, so this video looks at the rates of hydrolysis of different haloalkanes and how we can measure the rate using silver nitrate solution. So in the exam, we explain the rate of hydrolysis in terms of bond enthalpy. And I'm going to explain why we have different bond enthalpies for different carbon-halogen bonds. But you don't have to explain that, so I've grayed it out. So as you can see, since the atomic radius of the different halogens are different, so chlorine has the smallest atomic radius out of these three halogens, the distance between the nuclei of the carbon and chlorine and the shared pair of electrons is smaller for the chlorine. So the shared pair of electrons, which is the covalent bond, because a covalent bond is the attraction of the shared pair of electrons to the two nuclei of the atoms forming a bond. So the pair of electrons are attracting the nuclei of these two atoms together, because the electrons are negative and the nuclei are positive. Since that is the nature of the covalent bond, the greater the distance, so if I look at the carbon iodine bond, there's a greater distance between the nucleus of the iodine to the bonding pairs. So that greater distance means a reduced attraction between the nuclei and the bonding pair. So since there's a reduced attraction between the nuclei, or lower attraction between the nuclei of the carbon and iodine bond compared to carbon and chlorine, this would be a weaker bond, so less energy would be needed to break the carbon-iodine bond. So we use this term, bond enthalpy, so this is the term they will look for in the mark scheme. So in haloalkanes then, the carbon-iodine bond has the lowest bond enthalpy compared to the other halogens. So we haven't mentioned what bond enthalpy is before. Bond enthalpy is the energy needed to break a bond. So we look at enthalpy in more detail in another topic. In fact, it'll be the topic we do after haloalkanes. So bond enthalpy is the energy needed to break the bond, and the carbon-iodine bond has the lowest bond enthalpy because the least energy is needed to break that bond because it's the weakest. Now, in this reaction, we are going to compare the rates of hydrolysis. So I mentioned before, whenever we mention the rate or speed of a reaction, we must explain in terms of activation energy. So your answer must include the phrase activation energy. So we already had the fact that the carbon iodine bond has the lowest bond enthalpy. So for the iodoalkanes, they will have the lowest activation energy for hydrolysis. So hydrolysis of iodoalkane will have the lower activation energy than compared to chloroalkanes. So the rate of hydrolysis for iodoalkanes will be the highest as the reaction will be fastest. So here's a simple experiment to show the difference in rate of hydrolysis between two haloalkanes, and these two haloalkanes are identical except for the halogen that they contain. So they will have different carbon to halogen bond enthalpies, and will have different activation energies for the hydrolysis reaction, so they would go at different speeds. To make this a fair test, we put the two test tubes containing the haloalkane into a water bath to maintain the same temperature, as the temperature affects the rate the most. We hydrolyze the haloalkane by adding aqueous silver nitrate to both. The silver nitrate contains water, which helps with hydrolysis, and also the silver ions will help us identify which is the haloalkane that hydrolyzes first, and I'll explain that in a bit. We also need to add ethanol because the silver nitrate is ionic, and will dissolve best in polar solvents like water. But the haloalkane is largely non-polar, so will be fairly insoluble in aqueous solution. So the ethanol has a polar part and a non-polar part, so it would dissolve with the silver nitrate and the haloalkane. So the polar part will attract the ions and form ion dipole bonds, and the non-polar part will form attractions to the non-polar parts of the haloalkane. So what will happen when the mixture is added together, the haloalkane, so in this example I've just chosen the bromoalkane, will hydrolyze in water, and we have hydrogen bromide in this case formed, the hydrogen halide will be formed, and the hydrogen halide will ionize in the aqueous solution and form bromide ions in this case. So we form halide ions basically in both of these. So for the chloralkane, this will do the same thing, but in this case we'll have hydrogen chloride or HCl, and this will ionize to give us chloride ions, and the chloride ions will combine with silver ions from the silver nitrate, and we'll get a white precipitate for the chloralkane, whereas we'll get a cream precipitate of silver bromide for the bromoalkane. So not only have we got two different precipitates, but we should see the precipitate appear faster for the bromoalkane, because the carbon-bromine bond has a lower bond enthalpy than the carbon-chlorine bond, so therefore the activation energy of the haloalkane for bromoalkane is going to be lower, so the rate of hydrolysis, the rate of production of the hydrogen bromide will be faster, and therefore the production of the bromide ions will be faster, and therefore the formation of the silver bromide will be faster. So we'll see the silver bromide cream precipitate appear quicker than we would for the silver chloride. So just to repeat, the bromoalkane, in this case the bromopropane, will hydrolyze faster than the chloralkane. So the cream precipitate of silver bromide will appear quicker than the white precipitate of the silver chloride. This is because the bromide ions formed or produced from the hydrolysis of the bromoalkane will be faster than the chloride ions formed from the hydrolysis of the chloralkane. And this is due to the fact that the carbon-bromine bond will have a smaller or lower bond enthalpy than for the carbon-chlorine bond for this bond. So we've looked at how the rate of hydrolysis of different haloalkanes depends on the carbon to halogen bond strength or bond enthalpy. We also then looked at how we can measure the difference in rate of hydrolysis using a very simple experiment using silver nitrate and dissolve in ethanol. So next time we're going to look at the last part of this topic, which is the environmental issues related to chlorofluorocarbons, which are haloalkanes, on the effect of the ozone layer and how it breaks down the ozone layer. And we're going to look at the mechanism which this reaction undergoes, which is radical substitution.